Congratulations to everybody. We live in 2025, a time where everything is changing. We're beginning to unpick our own brains, quantum consciousness, microtubules, and their relationship to the quantum connected universe. And most of the world has gone public with the information UAP are real. Catch up, United States. In 2025, we have copious evidence that we're not alone in the universe. And good luck at keeping your job in a post-AI world. So we live in interesting times. Or is that just the Chinese curse? But there's one big, really big mystery, a piece of knowledge, a piece of information that is fundamental to all mankind. We're living in a fantasy. For over 100 years, every person on planet Earth has been lied to. And there's possibly no bigger lie than the Big Bang and the origin of the universe story.
In the explosion theory, we suppose that the matter in the universe was originally in a highly condensed state, which then expanded. And the galaxies which we now see are fragments of this explosion.
Perhaps like me, you grew up with the notion that the whole of the matter in the universe was created in one big bang at a particular time in the remote past. What I'm now going to tell you is that this is wrong.
Honestly, folks, science has got it wrong. But science is good at getting things wrong because it will change with new data. And in 2025, we have new information that the fairy tale, called the Big Bang Theory, is the wrong story. So today, join me on a journey trying to answer the biggest question of all mankind, the origin of the universe. That fundamental question that even science today admits that they haven't got quite right is being discussed by Dr. Bembry and DeLay. They've organized and invited a global team of scientists to discuss the true origin of the universe. It's the biggest fundamental question that we don't have all the answers to. And here's some breaking news. Myself and Chris Leto will both be attending the conference to bring you the latest ideas on the origin of our universe. I spoke to the two organizers of this conference and asked them this fundamental question. Why in 2025 have we got new information about the origin of the universe?
The newest thing, obviously, is the James Webb data, which is confirming some discrepancies between the way the age of the universe is estimated based on this Hubble expansion business, which we can talk about if you want. And also the presence of mature galaxies at a very, very early moments after the alleged birth of the universe. There's also just the pure mechanistic problem with how do you make something from nothing. That's a very questionably scientific proposal on its face as well. And so I don't think that's new. You know, Hoyle and the folks you were talking about argued about this for years. And it was actually, you know, this kind of eternal universe was really seriously entertained all the way up through the 80s. And of course, then the Big Bang kind of took its supremacy. But yeah, some of this new data is really changing things. And
which is kind of the case anytime that you have a new detector or you increase resolution. And I think that it's similar to what happened when we sent the first actual landed probes to Mars, because there's a lot of debate up until the point that we actually landed on the red planet about whether or not it was full of life.
Right.
Because you could see from a distance that there's seasonal changes to it. There was a darkening that people were like, oh, that must be the growing season. And so there was this real hope that we would arrive to find that the planet was verdant. And then we landed and it's this desolate wasteland and everything has to change in how we see things. And so I think that there's a story in science, which is that every time that you click over to a higher resolution, you suddenly start to see things that force you into retelling the story that you've been telling for decades previously.
And it's perfectly normal, right? Like the age of the universe has changed wildly in the last 100 years. Right. Nasti was researching it briefly the other day. What was it? Like, it just went from like 3 billion years to 6 billion years to 10 billion years. And, it seems like the higher resolution you get, the farther back you can see essentially, and things look more or less on par with how they do today, which is confusing for this expansion model. And then, I don't know if your viewers know this, but they thought the entire universe was the Milky Way galaxy less than 100 years ago, So like times change, more information, bigger, better, more accurate stories.
That's right. There are so many still unresolved mysteries about our universe, such as dark matter. 99% of our universe exists as a material that we don't know what it is. All that we know about dark matter is that it seems to exist because of its gravitational effects, but its exact composition and nature are still unknown. And then there's dark energy, apparently driving the accelerated expansion of the universe, but its origin and properties are also unclear. And of course, wonderful black holes. Today we do have some basic understanding, but many questions remain about their formation, behavior, and their effects on time. And one of the most enduring conundrums that might unlock the mysteries of UFOs is quantum gravity. Do advanced extraterrestrials harness quantum gravity to power their spaceships? But we still don't have a theory that unifies general relativity and quantum mechanics. We need to master that problem before we conquer space-time. Oh, this is so fascinating. I really like making these science films for you. But as an older bloke, there's one thing that I neglect, and that's hydration. I love sitting at this desk all day, researching, Zoom calls, and editing. And just like many blokes of my age, I tend to neglect keeping hydrated. So an amazing company called Holy have come to my rescue. This is their antioxidant and superfood iced tea drink. And cheers, they've just released a range of delicious milk shake drinks. Right now, Holy have a deluxe starter kit for you to try their energy drinks, their iced tea, or their hydration drinks, whatever you fancy. And very kindly, Holy are passing on these 2 discount codes. Yes, now that I'm rehydrated, we can talk about cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. But even that is not fully understood.
There's a central pillar to inflation theory, which is the red light shift. So things that are farther away appear redder, and the farther away they are, the more red they seem. And so the idea is that what that's telling us is that everything that's farther and farther away is accelerating away from us faster and faster and faster. Right. And so, okay, then
It's actually not a Doppler expansion. I'm sorry. I just want to make sure that we're absolutely accurate about this. They're actually saying that the wavelengths of the light are lengthening because the space itself is expanding. The universe itself is expanding, which is different from Doppler shifts, and mainly in that, there's ways to separate the two out. Let's leave it at that.
But I mean, go ahead.
No, absolutely. I mean, I think for the audience to understand the Doppler shift, people, of course, have heard it with passing sirens, but it also works in light and other EM frequencies. So coming towards you, higher frequencies, blue, are going away red. So you can tell things if they're going away. Yeah.
And it's worth noting, other people are are attempting, and over the years, obviously going back to Hoyle, people have tried to explain these redshifts, what they call the cosmic redshift, with other mechanisms besides the mere expansion of space. So there's been usually what they call tired light theories. So obviously a red light is more, well, maybe not so obvious, but red light is less energetic than blue light.
Yeah.
And so there may be other ways that as that light is relayed across, just enormous distances of intergalactic space, that it loses energy somehow. And so many people have attempted mathematical theories for how that might happen. We're going to have one of those, at least one gentleman who is an Indian scientist who's working on a tired light theory today, which is actually being taken halfway, as seriously as it could be taken, being antagonistic in some sense to the standard model of cosmology. So he's worked on the
tired light. I mean, we already have aged light, in the cosmic microwave background, where let there be light kind of moment where photons first produced are now retired into the microwave band. So obviously over time frequency shift. So that's great. I look forward to hearing his theories. Great.
Well, it's really interesting about the red light, the redshift is you really have to start to ask the question of like, what is light? How is it produced? What is happening to it as it's transmitted? And I think that cosmology actually in the red light shift starts to infringe upon the quantum world in some ways, right? Because like photons are fundamentally a quantum phenomenon. And if we don't understand what photons are,
the original quantum phenomenon.
Yeah, right? They're like the foundational basis of atomic behavior. And so if we don't really understand what photons are, if photons are these sort of weird little bowling balls that are pinging around the universe, then you can come up with one theory. But if photons are, let's say, an interaction between atoms, which is, have you come across the transactional interpretation of quantum mechanics?
Absolutely not.
So this is great. So there's a guy at Caltech whose name was Carver Mead.
Still is.
He's an emeritus professor at this point, and he splits his time between, I think, Seattle and Pasadena, and so he's older now, and he spends less of his time in the flow of research. But he was associated with John Kramer of, I think, the University of Washington, and they basically started to think about the strange time reversals that are apparent in, like, Bell's inequality and a lot of quantum experiments.
He was an acolyte of Richard Feynman at Caltech, and so Feynman came up with these time diagrams and so forth, which I think he was trying to use to explain how two atoms are actually involved in the transaction of light. So there's an equalization of energy between two atoms, which is apparent in any emission and absorption relationship.
And so if you can have photons without atoms, then you come up with an explanation for redshift and the cosmic microwave background radiation that's kind of this like immaterial thing where there's just these photons that are floating around. Yeah. But you can also say that, okay, a photon is actually a transaction between two atoms. It is literally a communication back and forth between them. And that creates a material basis for actually trying to figure out what is light and what causes it to be redshifted. And if photons can only travel through the relay event between atoms, then all of a sudden you have that, okay, so you have this vast expanse of space that light is traveling across, and as it travels, there's a tiny bit of energy lost in each relay. Because, so you have a photon that hits an atom, it excites it, and then that atom sends it along the next path, but a little bit is lost in that transaction. And so over the course of the billions, trillions of transactions that happen from the edge of the visible universe to here, things slow down. And so you don't necessarily have to have this weird thing, because what does it mean for space to expand?
A really specific example of a really general problem in science as a whole, but especially physics, which is where you take ideas instead of physical substances, and you apply physical processes to ideas, which is, the philosophers know this as the fallacy of reification. Right. But the reality is, like, I can't take some love from my wife and warp it and hand it back to her. It has no physical significance. Right. So when we talk about an idea like space, which is a coordinate system of locations, when we take that coordinate system and start talking about this idea being warped, we've kind of departed from physics, as far as I can tell. So that's just a much broader.
No, that's a great broad point. I mean, I've often interviewed physicists, and I always start with the question, "What's physics?" And and it's basically good ideas that change, and some of them are quite arrogant and say it's everything, but it's only a human definition of ideas. And as you absolutely right. I mean, ideas should be overturned with new data and experiments, and good.
And rethinking the old data, that's a huge piece of the puzzle too.
Yeah, absolutely. So you two are doing something amazing in this brave new world of redefining the Big Bang, or the origin stories, and everything to do with the universe. You're going to have a conference in Portugal coming up. So when's that? And tell us about it.
We're getting together this summer. It's June 12th to the 16th, and there've been a number of voices in the dissident discussion about the origins of the universe and the Big Bang and the Standard Model, both within the academy and outside of the academy. Yeah. So we're bringing together a number of those people. We're bringing together people who spend a lot of time looking through telescopes, people who examine the Standard Model and try to, repair it, essentially. And then complete heretics who think that the Big Bang never happened, for instance, or that the basis for redshift and the basis of the CMB are not as thought, and really approach these in different ways. And we really just want to have a conversation. We want to get these different people together in a way that's not adversarial, but is really aiming to understand what we're looking at. And honestly, it's part of a bigger project where we really want to revive the spirit of the Royal Society from the 19th century, where lots of ideas can be on the table. Literally, we can just sit there at a table and talk about completely different perspectives on an issue without throwing coffee in each other's face, and see if we can actually make some progress. Because, even if you hate 99% of somebody's idea, they might have 1% that'll really help you along. So that's kind of our core ethos, I suppose.
Yeah. And I think that to add to what Shiloh said, there's this real damaging vibe in science, which is that someone is going to arrive at truth. And that truth is going to be with a capital T, and then we will take that set of facts and we will put it in our pocket, and from here on out, we will know something with dead certainty. And the more time that I spend thinking about science, the more time that I spend reading papers in, biology, geology, archaeology, physics, the more that I realize that I have a feeling that it's almost impossible to come up with a single model that encompasses everything. And so physics, astrophysics and cosmology especially, has been obsessed with this idea of a final theory that is going to be set upon the table and we never have to mess with it again. And I think that that's a totally deadly perspective to have for science, because we're always going to be finding new details. As we see new things, we're going to have to figure out how to explain them. And to have an atmosphere where everybody has a little bit of humility and recognizes that, hey, the idea that I have might apply here, but somebody else's might apply over there, is what we need. And we're really trying to cultivate that. And so that's why we're bringing all of these different people together and very, very clearly emphasizing that this isn't a debate. This is not somebody who's going to walk away the victor with the spoils of scientific reputation.
Good.
I think it's pretty historic.
I think the whole field has always been fraught with controversy. I mean, it seems to be the Big Bang, the origin of the universe, has always been a competitive field, whereas in fact, my expansion theory is better than yours, mate. And it seems a bit silly. So yeah, no, I think we're living in an age with new data, and it needs to be discussed around the table.
Well, Shiloh's teaching this astrophysics and cosmology course at the university right now, and he's doing a really interesting thing where he's integrating myth and legend of various cultures over time and how they've related to the cosmos. And
right.
Like I've heard you over the course of the last several months slowly starting to formulate this real sense of, I don't want to say outrage, but you're just really perplexed at the idea that cosmology even became something that was owned by the scientists.
By the physicists in particular. Like historically, a cosmology is how we relate to the universe. I mean, not just the stars, but everything, basically. Like, what are we doing here and what is going on? And it's interesting that over the course of the Western industrial progression, that task would be relegated purely to the realm of physics, right? Because there's, I don't know about you, but my life doesn't involve that much physics on a daily basis. Like I have relationships with people. I love music. I love podcasting. Sure. There's so much going on that's not physical, right? And that seems to have been necessarily removed from the discussion when you hand off something like cosmology to the physicists, which is just wildly perplexing that even happened in the first place, because you tell very different stories depending on who you put in charge of telling the story. And so a physical story of the universe, I don't know that it can possibly capture the universe.
Absolutely. I mean, physics is purely one aspect of the universe. And I like it. That's a really good approach. I mean, there's so many origin legends. I think they're absolutely fascinating, and they served a purpose in their culture, which was satisfying or inspiring. So why does it have to just be physics and mathematics? You're quite right. Oh, that's a really good course to teach. Your students are very lucky. I like it.
They like that stuff more than the hardcore astrophysics. It's a lot less math.
Well,
try to give them a break every once in a while.
It's so funny because I feel like what you said about, we have all these cultures that had mythological origin stories that told you something about how to live your life or some significant legend that gave you meaning. And I actually think that the transition of cosmology from a mythological story to a scientific story is a readout of the metaphysical necessity of a worldview to have an origin story, to be an acceptable worldview.
There's another whole aspect of the creation story that possibly cosmology doesn't address, and that is myths and legends. Throughout the history of humanity, every culture has come up with an origin story. Where did we come from? I think to just dismiss those stories as silly legends is a big mistake. Maybe we can discover hidden truths by looking at the myths of our ancestors.
Every culture that has a set of myths and legends also has to have an origin story in order to be able to say that it is a complete worldview. Because if you have that, I don't actually know these legends, but the spider god brought the moon down, and Coyote brought the waters, and Baba Yaga lives in the woods and eats children that wander away. You also have to have something that answers the question of okay, well, how did everything get here? Because right? Like
That's like the third question out of a child's mouth after you tell them about the other three.
Yeah, exactly. And so you're like, okay, well, you see all of these things that are in front of you. I have a reason for how they work. And then the question is, well, okay, well, how did they get here? And you're like, okay, well, I have this story of something that happened a long time ago, really far away, and there's no real way for you to see it or to know it because the players that were a part of it weren't of this world. And so that's the origin. And it creates kind of this feeling of relaxation because you're like, okay, well, it's a complete story. And as we went from being a culture that was more preoccupied with religion and became one that was more preoccupied with science, science began to have all of these stories of, you know, how the sun works and how the moon works and how the earth works and and atoms and light and electricity and all these things. Yeah. And then finally you get to a place where you're like, well, how did it all begin? And you're like, oh, well, God made it? And that's unsatisfying. So you have to create some kind of scientific origin story. You have to have a field of cosmology because you cannot place your faith in science as a belief system about the way that the world works if it lacks the origin.
But it failed. I mean, people, it only goes so far. I mean, obviously, geniuses like Stephen Hawking, who says it doesn't require a start, it doesn't require an origin, it doesn't require God, is a kind of an interesting. But I think the general public kind of listen to the science and think that probably the universe is expanding if they even know that. But science doesn't answer the big question. I mean, I get this all the time. They're going, people are let down by physics, but by astrophysics, because it dicks around with the later bits, and it doesn't answer the bit that we all kind of want. Whereas myths, legends, and religion can go there, but it's really hard for science to kind of go. There was a finger on the button, it's difficult stuff.
But by the way, I don't know if people realize this, but the original conception of this expanding universe, this Big Bang, before it was given the name Big Bang, was actually developed by a Jesuit priest who was also a mathematician. Mm-hmm. And, in some sense, you can speculate that in his mind, he was resolving, how do we bring this age-old myth into a scientific world for the first time? And whether he meant to do that or not, consciously or subconsciously, it certainly had that effect of really, let there be light, rescuing this Judeo-Christian narrative and bringing it into the 20th century to the extent that he had to famously talk the Pope out of trumping it up so much because it was embarrassing his scientific face. So that's kind of an interesting little tidbit about the whole
I know
story.
People forget about him, and it's great. Belgium, I mean, brilliant, absolutely fantastic, and I think 20th century science took over and looked at some of the practical things, but as I said, I don't think it ever addressed the big fundamental problem. I mean, I think it was addressed by certain people who wanted to go there, but they were dealing with theories, whereas most of the Big Bang seems to be a bit quite practical, really measuring stuff. I think we're living in a vacuum really at present. I think it does need redefining, and I think as new data is coming out, I think it's good. We want to push those boundaries back.
I think one of the hardest pieces of the whole paradigm shift is reevaluating the early pieces of the story, not just the new data that's coming out, but I mean, obviously, as a theory begins to weaken, new data won't fit as well as you'd hoped it would, and that's a huge piece of the puzzle. But there's also this layer of assumptions that's built into astrophysics, well, really into all science, but it's probably nowhere more apparent than in cosmology and astrophysics. Everything from estimating distances to estimating the meaning or interpreting the meaning of this black body spectrum that you see everywhere in the sky. these have assumptions involved in them. And as you move further down the road generationally as scientists, people tend to accept assumptions without really revisiting why they were assumed in the first place. And that's a place where you introduce a lot of noise into the system. And you also get further away from being able to make corrections that could be foundational. I think people forget that we don't have test tubes in astronomy. All we have is light, right? We just look up at the sky and we take some light and we try to come up with stories that make sense about what that light means. And so almost everything is an indirect measurement at the end of the day, other than just the light from the telescopes, right? So the distances, for the most part, are built on a tower of assumptions. We call it the distance ladder. Of course, the redshift, like we talked about, we assume, the big assumption is that the only way light could redden in this like achromatic way, so across all the colors, would be through the expansion of space. That's an assumption,
Yep.
So there's this tower of assumptions, and there's huge ones at the core of the CMB, and I would love to talk about that at some point. I don't know if you want to wait for Chris to get here first, because that's the part I'm most excited about, let's say.
Well, same here. I mean, I think I've always kind of slightly copped out and been very much kind of in the science world and kind of believed assumptions and taken them. But the one part of the origin story of the universe where I can go back to is the CMB, cosmic microwave background, its discovery and its revelation when we saw detail in it. I think it's just the best story ever. I mean, I think this discovering microwaves and Penzias and Wilson and then Princeton coming up with an idea of what it was is just absolutely probably the best physics story, along with the hunt for planet Vulcan. Those two stories are my favorite ever.
It is one of the best physics stories. I think that's what makes it the most difficult to interrogate with any sort of skepticism. And right. Nobel Prizes were given very quickly. I would actually peg that as the moment when cosmology was duly accepted by the scientific community as a bona fide science for the first time. So it's huge.
That's the place where it got data for the first time, right?
Like high quality, yes. I mean, let's make no bones about it. The first recording of the microwave background shows an incredibly noise-free black body spectrum. More or less. Assumed to be essentially right above where this telescope was pointed on the coast of New Jersey. And then they sent up balloons. They saw it with even greater resolution. They eventually put a satellite into near-Earth orbit, saw the same thing, and so on and so forth. So it's definitely a really high-resolution pile of data. The question then becomes, what is it? What's really interesting about that story is that the what is it essentially appeared immediately. Actually, I believe that the paper was published in the same
either in the same volume or the next issue.
So it wasn't like they were like, hey, we saw this crazy microwave signal. It appears to be a perfect black body spectrum. And we should talk about black bodies in a second, but they immediately were like, oh, it's the echo of the Big Bang. So it was decided almost instantaneously. It's sort of like when you have like a shady assassination attempt and they're like, it was that guy. And you're like, what? Wait a second. Can we talk about this for a second? There was none of that. So that's really an interesting piece of the puzzle.
Oh, that is fascinating. Yeah, I mean, we know the story of Penzias and Wilson and Bell Labs and the pigeons and Telstar, and I think that's actually great. But they didn't obviously know what it was. But so when the department in Princeton said, we know what it probably is, it wasn't questioned. It was just like, oh, good.
Yeah, not in the least.
Right.
And that might not seem like that big of a deal on its face, right? If the Big Bang theory was in existence, it wasn't called that.
Right.
But there's one real crux of the puzzle, which is the most disturbing element of all of this. And there's a lot to unpack about it. But The puzzle is that black body radiation is the kind of light given off when you heat up a body, like a solid body or a liquid body, something that has actual bonding between the atoms involved, right?
Yeah.
You get this continuous rainbow of light when you put it through a prism. What's interesting is you don't get that from ionized gases, right? So individual atoms, they don't have the articulation to one another to give all these overtones of electromagnetic radiation.
They're just one, yeah.
They're just little lines, exactly. So, you can just check out pictures where people have done these comparisons. It's anybody can, with a prism, can look at an incandescent light bulb versus a compact fluorescent and see basically what I'm talking about. Compact fluorescents are not perfect because they actually have some fluorescence involved, and the anode and cathode give off some black body radiation and so forth.
But they're still an ionized gas, right?
For the most part, yeah. Which is
fluorescence, right?
Right. So you can look up pictures of gas, like actual gas lamps, like hydrogen lamps and so forth. They give off individual frequencies. And so, if we start to unpack this story about the CMB, we're told that this light comes from an ionized gas, and that when we ask, well, how in the world would an ionized gas give a black body spectrum? The answer is that it's a smearing of myriad different processes that led it to this exact fingerprint signature that you get from a black body. And the reality is that it's not a smeared picture. It's one of the most precise black bodies ever recorded. Like you can only get such a beautiful black body spectrum from heating up a soot-covered chamber and essentially exposing it to a prism in the same way. So this is not just a sort of approximate black body. It is an incredibly perfect black body. And we have no real physical evidence on Earth or any laboratory experiments that would lead us to believe that that thing could be accomplished by anything other than a solid body or a liquid body. Now, when you explain this to an astrophysicist, first of all, they kind of laugh at you, but they also would say, well, obviously the stars, which are gaseous plasma, give perfect black bodies as well. And they sort of rest on that. And then you say, well, why do you think that the stars are gaseous plasma? And then you get into a really interesting discussion.
That's right.
And that discussion starts to unveil an even more exciting paradigm shift, which is at the heart of all of astrophysics and all of cosmology, which is, what is the material basis of the stars? We know they're made out of hydrogen and helium, but is it in a solid or liquid form, or is it actually in a gaseous form, as we're told? Because if it's in a solid or liquid form, and there's some really interesting evidence that's amounted lately concerning well, let's get to that in a second. If it's in that solid or liquid form, then you have a completely different story to tell about the stars, about the origin of the universe, about literally everything, about compact objects like black holes and white dwarfs.
Right.
And if you try to understand why people think that the stars are gaseous plasma, you have to go all the way back 100 years to the Royal Society, where people are actually debating it. And they run into a lot of trouble. Like, they can't figure out how to power the stars at the end of the day without it being a gas. And this gentleman named Arthur Eddington steps up to the plate and knocks it out of the park with his theory of gaseous fusion, and ends up developing the equations of state necessary to make a star power itself using a gaseous plasma. And it was wildly successful from a mathematical standpoint, and it solved a problem that all of those great minds could not solve. They tried everything on. They tried nuclear fission. They tried compression, like diesel compression, essentially. They tried all this stuff. Nothing worked. But the gaseous fusion theory seemed to satisfy it in such a way that it could potentially lead to a long-lived star. And so there was some other, a bunch of different pieces of the puzzle going on at that point in time. But the one thing they didn't have access to that we're starting to have access to now is the enhanced phase diagram of hydrogen. So, of course, the star is primarily made out of hydrogen. Right. And what they didn't realize in that day was that if you compress and heat hydrogen sufficiently, at some point it becomes an actual liquid metal of sorts.
Oh, yeah, sure.
And they're beginning to think about this in terms of Jupiter and so forth. What's really interesting is, of course, the sun, could be argued that at its surface, it doesn't have the pressures and temperatures necessary for liquid metallic hydrogen. But what's really interesting is that it does below the surface. And what's even more interesting is that liquid metallic hydrogen is showing evidence of being metastable. In other words, when it's formed, it can exist for periods of time before it degrades and sublimates when it's relieved of pressure and temperature. So we see this bubbling up at the sun's surface. There's every reason to believe that these metallic forms of hydrogen could be present at the surface and could very easily explain the black body spectrum in a way that doesn't resort to cobbling together a bunch of random processes to somehow deliver this incredibly perfect fingerprint that we only see from heated bodies and liquids.
It's kind of an Occam's razor situation, right? Because you either have a statistical mechanics explanation, because inside of the sun, currently, the production of the perfect black body is due to photons bouncing around inside the sun for millions and millions of years until they emerge at the surface in a form that happens to have this Planckian spectrum. And so that's the conventional explanation, which requires a lot of assumptions and requires a lot of statistically perfect interactions to give you the result that you see, versus a black body explanation, which is that you have a lattice that is hot, that is actually producing this. And it seems like the rule for scientific theories is in some ways simplicity. Like, if you can have a theory that offers you a simpler explanation, that's probably the one that you want to use.
Yeah, we're just saying, hey, if it looks like a black body, it might actually be a black body. That's all.
Why not?
Right?
Why not?
Right. And by the way, like, shout out the guy who's done the lion's share of work on this project. His name is Dr. Pierre-Marie Robitaille. He was the longstanding chair of the Ohio State, I believe it was the radiology department. So he worked on advancing the power of MRI machines at the time. And a lot of people think that's weird because he's like done all this astronomy work in recent years. But really, if you think about what MRI machines are doing, like, it's electromagnetic radiation analysis, right? And so he was kind of the first person to really revamp these ideas from the 19th century and say, wait a second, guys, what are we doing? Like, the sun doesn't behave like a gaseous plasma. Maybe we shouldn't build our entire pyramid on that assumption after all. And I don't know. He's had a rough go at it. People don't like him too much, as you can imagine, inside the academy.
But in some ways, humans are, I often say this, we're clever bunnies. I mean, what we're actually, when we build airplanes, when we build iPods or whatever, we're using energy, we're using stable matter in a way that we perceive it in reality. I mean, I think we don't understand. But we just build models that work for us. So if it works, just keep going, and that's how I really see physics. Is it's good enough until it's proved wrong. But I think science. I think what you're saying. I think science tends to hang on to the good enough for too long as competing theories come along.
I'm really glad you brought that up, because if you think about what is the utility. Like, who cares, like, about any of this ultimately? Like, does having a cosmology lead to better technology? Like, maybe not, but there is one interesting overlap with all of this, which is fusion technology.
Right.
The idea of a fusion reactor is we're going to build a baby sun on the Earth, and we're going to use it to power our civilization with cheap, clean energy for all of time. I don't know if you've noticed, but it seems like we're 10 years away from having a stable fusion reactor for about the last 50 years.
30 years, yeah.
Right. And so all of this technology is based around a conception of a gaseous star. They're trying to confine gaseous plasma inside of magnets and make fusion reactions happen. If the stars are not doing fusion using gaseous plasma, which really doesn't seem like they are, how are they doing it? And so there's been some really quiet papers released with blanket NASA funding, there's one group out in a laboratory in Cleveland. It's escaping my name. It's a NASA laboratory. It's published on this idea of solid state fusion, which is essentially impregnating metals with deuterium, applying. This is at ambient temperatures, by the way. This is not at gazillions of degrees. And you sort of squish it a little bit. And you use the lattice of the metal to do the confinements, right? You're not trying to like hold this plasma still and do all this huge, difficult, expensive, energy costly work. You literally use the metal lattice to hold the substrate in place. You squish it with a laser and you get fusion gains, which from the initial papers seem really quite reasonable, at least compared to all of this work coming out of the tokamaks and so forth. We've tried many, many times to get these NASA people on our show to talk about it. We've had other NASA scientists on the show, no problem. Nobody will talk to us about this. So for me, I'm like, oh, you guys are onto something over there about this, because they do not want to come to the table about it. So it does have real world ramifications potentially if we come to understand the stars more properly.
I think the most recent attempt was the funniest, because we reached out to the laboratory and then got intercepted by a NASA bureaucrat. And the NASA bureaucrat was like, well, they're not really part of NASA anymore.
Oh, great.
And you're like, why are you answering their emails for them then? She's like, so they've declined to speak to you, but you can look at these brochures that we have on the subject if you'd like.
That's really fascinating. Good. So, who else are you having in Portugal at your conference?
So our slate is, like Shiloh said, theorists, observationalists, critics, and philosophers. And so we have representatives of a bunch of different perspectives for all of these. And so the most probably well-known of the bunch is Eric Lerner, who wrote a book in the 90s called The Big Bang Never Happened. He's working actually on a fusion project in New Jersey, and has been this thorn in the side of the scientific establishment for decades at this point, because he's always going around and he's like, I don't think this happened. And so he's coming. We have...
That's the book that got me all into it when I was... just threw me into this mess when I was 11 years old or something,
Right, Eric's
book,
right.
And he has this like really fantastic introduction to the book, which really, I think if you don't read the entire book, you should read the introduction, because he really lays out how the structure of society informs the way that we see the world, and how important it is to see the world clearly. And so I think that he has really, really deep insights on this. Then from the sort of the critics and the, I'd say, more philosophers of science, we have Gareth Samuel of See the Pattern. Right. We have Alexander Unziker of Unziker's Real Physics. And so these are both guys that spend all of their time digging through the data and trying to figure out what it actually says. Where have people gone wrong? What have they seen that isn't accurate? How have they misinterpreted it? And we're pairing them with at least two people that I would say are kind of in the mainstream. So we have C.S. Unikrishnan from the Tata Institute of Technology at, I think it's in Bangalore in India. He works on the Indian branch of LIGO, so the gravitational wave detection.
Oh, great.
But he is, even in that space, a little bit heretical, because he thinks that we've fundamentally misunderstood relativity. And so he does a lot of stuff on variable speed of light, and the fact that perhaps Einstein wasn't totally correct. Right. And we have Indranil Banik, who is, we call him our paradigm repair guy, where he's a lambda CDM. So he studies the standard cosmology, and is early career where he recognizes that all of this is about to shift, but he's very cautious about where exactly he's going to put his foot down in terms of what he thinks is correct. But he has this encyclopedic knowledge of the field. And so if somebody's like, hey, we see this and this is what it means, we have him there to be like, well, actually, we see this other thing. So we need somebody who's acting as the representative of what is consensus. Because if we're going to be...
Martin too, right?
Oh, yeah. Martin Corredoro, he's at Tenerife. And he's wild. Like, he's a playwright, he's a philosopher of science, and he's also an observational cosmologist. And so he's spent his entire life looking through telescopes and thinking about how all of these things fit together. He knows all of the different models and their pluses and minuses. And so they're kind of our standard guides. And then we have Andre Coque Torres de Assis, who's at the University of Campinas in Brazil. And do you know him? He does he's done a ton of stuff on electrodynamics and electromagnetic theory. Okay. As he's like been translating old texts to show that there's all of these intricacies in the way that current runs through circuits and how electricity and magnetism interact that we've glossed over in our technological push towards the grand vision of the future that we're building. Sure. But he's also a Machian cosmologist. And so he's trying to bring in these older texts that are trying to explain things like inertia on the basis of an interconnected universe and the interconnection between atoms being brought to bear on the things that we see here. And so it's this very deeply material interpretation of the world, which is like, no, the things that we see here aren't just arbitrary field effects. There's real interactions that are leading to the things that we observe. And then we have the slate is just incredible.
We also so just newly added to the roster, we have a gentleman who works on liquid plasmas. Actually, Patrick Van Reyes. He's been on the show before too. He and I will be attacking the problem of the liquid sun and representing some of Pierre Marie's work. But also Patrick's out there doing experiments about it, and his advisor in grad school, Bogarts. Actually, one of a very prominent plasma physicists gave a shout out recently in a review to the shifting paradigm of the liquid sun, which I took as a really good sign. So he's hard at work in the laboratory on demonstrating how you can actually have plasmas in the liquid form. So he's kind of saving that word plasma. But I can see he's kind of giving an olive branch to mainstream astronomy from what I can tell, because he's like, no, look, like it can be a liquid and a plasma, and you guys can keep the word plasma, but we have to think about things differently. So really excited to get him out there.
And then Mike McCullough. So Mike McCullough is the originator of quantized inertia, where he's working on these inertial propulsion systems based on the Casimir effect. I will be honest, the last time that we dug into his ideas was probably like 2 years ago at this point, and so I can't represent his perspective.
He's bringing a really I haven't read his papers on this yet, but he has this notion he calls applied cosmology. So we'll find out more about that. But he seems to think that there's practical material value in cosmological sciences. So I'm looking forward to learning more about that.
But it's going to be, and the way that we're organizing it is that we're basically like each day of the conference is a different pillar of the cosmological paradigm. And then we have talks in the morning where the people that are thinking about these topics will give, like half-hour talks with a half-hour question and answer session. And then in the evenings, we're going to have panels where we bring them together. And so over dinner, we eat while they discuss. And
then it gives people the afternoon to kind of enjoy seaside Portugal. And, hopefully these theorists will be taking walks on the beach together and like figuring it out. That's the goal. It's really like, this is a legitimate meeting of minds. I actually think it's a historic meeting of minds. If people come in attendance, that's gravy. But ultimately, like, this is a actual scientific interaction for these people. And so we kind of set it up for them, for the presenters, to be able to do science while they're there.
And we're kind of pushing them also to make their research accessible. Because I think that one of the biggest challenges with something like cosmology and astrophysics is that somebody starts talking and then it's just seas of equations that are being brought to bear on the presentation. And I'm like, you guys can't do that. Like, you have to talk in English so that people can understand what you're actually saying and why it's important. Because it's not just for you to talk to each other. This is literally something we want to bring to the world so that everyone can see what it looks like when a paradigm starts to ratchet to the new way of seeing things.
Oh, it's great. So I really hope to be there, and it'll be brilliant to meet all your guests and meet you two in person. And my background is very much turning that those equation bunnies into practical speak. And sometimes it's really hard. I've certainly struggled with a few people, but no. I'm very excited to see what comes out of beachside soirees over lunch in Portugal. It's so good. So before we finish, tell us who you two are and what do you do and what's your background. And what a brilliant idea, by the way. The conference sounds fantastic. Can't wait to see you.
I think it's going to be really good, yeah. I mean, Shiloh and I are dyed-in-the-wool nerdlings. We spent decades in research laboratories. I studied everything from reproductive medicine to tuberculosis to aging research. I got my PhD in electrical communication in bacterial systems. Shiloh got his PhD in the biophysics of water inside of nanoscale confinement. He actually published in Nature last year, which is really exciting. And we tell this spiel a lot when we meet people for the podcast and we're, interacting with them for the first time. But we came up through the academy. We were really trained super intensely to think about single questions, because that's kind of how science works. You show up to a lab, you're given a topic, and almost everybody that we worked with who was our supervisors, like our PIs, our professors, were people who had taken the work that they had done in graduate school and then had just continued to ask questions about that, right? So it's you get to grad school, you have a PI, you train under this person, they hand you a subset of their questions, and then you go out into the world and you continue asking questions about that system.
Yeah.
And we were like, that is not how we want to spend the rest of our lives. Like, science is so much bigger than this narrow inquiry. And we really wanted to help science grow and develop and change, because we saw, even when we were in grad school, how political it was to get an idea accepted into an academic journal. Mm-hmm. How academics would talk behind closed doors in ways that they would never speak in public, in the sense of true, doubts about the paradigms or questions that they had that they were like, well, I could never ask this question in my research because I could never get funding. Right. And it seemed like there was a place that was missing for them to come together and to actually have open discussion, where they weren't afraid of what somebody would think or what their peer review would say. Yeah. And this is what the Demystify Sci podcast is. This is what the conferences are. It's an opportunity for people to come together who think so deeply about these questions to actually speak freely with each other in an atmosphere that encourages them to think as creatively and as deeply as possible, as opposed to in this line of thought of like, well, this is what the grant will let me do.
Before we go, if people are interested in finding out more about what we do at the podcast or about the conference, go over to demystifysci.com and check out the links we have there. It should be easy to find your way. If you want to attend the conference, you can figure out how to do that quite easily. And we would love to see you at either one of these places. Thank you so much for having us, Simon. And we're looking forward to seeing you in Portugal, too.
Thank you very much, Charlotte and Anastasia. That's really interesting. Guess who we have? We have Chris. Hi, Chris Leto. How are you today?
Hi, Simon. I'm doing great. Thanks for having me back.
And what's going to be really exciting is you and I are going to meet up face to face for the first time and actually discuss the origin of the universe. So is the origin of the universe a subject which keeps you awake at night?
It does, actually. I guess I'm one of the few. Hopefully there's more people out there that actually do consider this stuff. But like, I'm not even joking. I was thinking about it last night. I think our science is totally broken. I published another video that we'll be releasing later this week on really how our physics is totally broken. And I think it goes back to our fundamental assumptions. And I think one of them is the whole Big Bang and is the universe expanding? I think we really need to look into it.
Yes, I think the most interesting takeaway from the chat that you've just heard for me was that science has kind of imposed a thought idea, which is obviously wrong. They didn't know, but they have been very close to looking at new ideas. And I think now in 2025, when we have got new data from the James Webb Space Telescope, has looked into the past and seen fully formed galaxies and stars, we expected to see baby stars and proto galaxies, but no. So the date is wrong. And because of that, I think science, as it does, needs to look at the new data and come up with some better ideas. So we're going to meet up.
I'm excited. I'm gonna pick you up from the airport, actually.
Oh,
I'm
that's
looking
really...
forward to it. Yeah.
Sure.
I'm excited. Yeah,
Yeah.
I'll collect you at the airport, and then we can go towards Setúbal. It's in Portugal. I saw that the conference was going on in Portugal, and so I immediately signed up without even asking anyone in my family. I just bought tickets and I'm going.
Brilliant.
So I'm excited. I'm glad you're going as well, Simon.
Yeah, I mean, I live in France, and it's I will fly down in my F-16. No, I won't. I'll fly down on EasyJet to Lisbon, and then the conference is in the middle of June. So anybody who would also like to join us, you're very welcome. There's tickets available now, and some really good world leading scientists are going to be there discussing other possibilities of the biggest question for mankind, the origin of the universe.
Eric Lerner, I've been following him for a few years, as well as Alexander Unzicker. He's my physics hero on YouTube. He has an amazing channel, as well as See the Pattern. I literally watch all their YouTube channels, and then they're going. Like I said, I signed up immediately. And Portugal is beautiful in June. I mean, it's a beautiful country, but June is the best time to come. So I think you're going to have a great time, Simon. Yeah, anyone else that wants to come meet us in person. I think it'd be really exciting conference.
Sure. We're going to take over the seaside town and talk about good stuff, eat good food, and hang out. The structure of the day is going to be a speaker in the morning, and then the middle of the day is we're all going to walk along the beach or along the esplanade and debate what we've learned and our ideas. And then in the evening, in a very traditional way, we're all going to get together around a round table and have a bit of a discussion. And we're not going to come up with, this is the new story. We're just going to discuss it. So Chris and I are going to blog, whatever that is, during the event, obviously hang out together and meet these interesting people. Hopefully we can collar some of the ones that we want to speak to and do some interviews in the bar. So that Chris, it's really exciting. I'm looking forward to visiting Portugal and of course meeting you and solving the mystery of the universe.
I think it's the bleeding edge of science. If you look at our current cosmology, we've been in a crisis of cosmology for like 2 decades. Yeah. And they keep saying maybe there's a crisis. Maybe we should look at our actual models, and then they never actually go and look at their models. So I'm really excited to be around a group of people that have been looking into new models, for decades. And so I think it's the bleeding edge of science. It's right on the frontier. I'm super excited. It's super nerdy, but I love it, man. I'm stoked.
It's good being super nerdy, and it's such a brilliant subject. So thank you, Chris. It's good to see you today. And I'm looking forward to being at the conference and hanging out with you. Cheers, and a good pint of whatever you drink in Portugal.
Cheers, mate. Sagres.
Oh, great.
Sin alcohol. Yeah.
Fantastic. All right. Thank you, Chris.
All right. Thanks, Simon.